All right, so yeah, homework clarifications. On question 2, I don't want you to just write out the numbers from 10 to 99 and answer the questions, right? I want you to use sum or product rule or something like what we've been talking about. On question 3, the goal is to simply have one matching pair. It doesn't have to be a particular color. It's not how many socks do you have to grab until you get a matching pair of red socks. Because you might never get a matching pair of red socks. You might just keep grabbing blue and green socks. Okay? But eventually, if you grab enough socks, you will have a matching pair. Okay? And it might happen after only 2, or it might take more. So the question is, what's the minimum number of times that you need to pull a sock to guarantee that you have at least one matching pair? And if you pull 100 socks out, you're guaranteed to have at least one matching pair, but you don't actually need 100. The answer is smaller than that. Sage?
You answered it.
Okay.
Can we talk about number 1 a little bit?
Yeah.
Like, for some reason, the only thing that I could really come up with was the sort of like formula thing.
Mm-hmm.
I wasn't sure if I did the recurrence relation right.
What did you come up with?
I think it was like for some reason I feel like all I can think about is the whole actual formula.
Yeah,
I
so
don't necessarily say it, but
so the initial population is 25. Population at time 2 is
25 times 3.
yeah. Population at time 4 is
Yeah.
triple that. Population at time 6 is right.
And then-
So you're finding a formula that jumps out from that.
Right.
But to describe,
So like at the previous 2 hours times 3, basically?
yeah, basically something like that.
Yeah, okay. That's maybe that's I was thinking it was more complicated or something.
Can be that simple. And if we really want it to be a recurrence relation, maybe we need like to use 2n instead of n. But we can define it in terms of an element 2 spots earlier. That's fine. And then your initial condition, P0 is 25. Already got that. And then the general formula jumps out.
So it's not like Fibonacci's, you don't have 25 plus 3 multiplied by 25, you just have 3 multiplied by 25.
Yeah, we're told that this population is triple whatever this population was.
Okay.
So that's just going up by 3.
So do you just want us to only deal with P of multiples of 2?
It's not really defined what happens in between, say, 2 hours and 4 hours. So I would just do it for even numbers. I mean, presumably it's growing in between there and we can find a formula for it, but then it's not discrete math anymore. It's continuous math. Found a pineapple in the kitchen this weekend. Counting. It's like, let's cut that out the other end.
Did it work?
It seemed to be 13 every time, no matter which way I went. I thought it was supposed to be different in both directions. But it wasn't always clear exactly if you were on the path. Because sometimes they meant like vertex to vertex instead of like edge to edge. But it seemed to be a pretty consistent 13. It came from Freddy's, so maybe it's like a mute or something.
One of those undesirable fruits. they sell in France.
Yeah. All right, any other questions? So I think 2 people for their programming assignment, turned in the C code, but did not turn in a PDF showing the output. So if you're one of those people, or if you didn't turn in your assignment at all, email it to me today. Okay, if I get it before midnight, I'll go ahead and put it in.
So what's that? So are we supposed to contain our source code in the PDF?
Yes,
Okay, good.
and that's what most people did. But when I first made the assignment, it was a .c file only, because I messed up. And so you change your PDF to a .c. And then I didn't think I could get rid of the .c because I was afraid it would delete your submission. So it's set to take .cs or .pdfs, but some people did a .c. So,
Sometimes following directions is hard.
yeah, it's all the details. So yeah, just shoot me an email with that. That would be good. All right, if it wasn't clear at the end of Friday's lecture when we were talking about Wallace Trees, the real punchline there was that when you use a carry save adder, you can process the first bit of all your numbers without worrying about any of the other bits. And you can process the second bit of all your numbers without worrying about any of the other bits. And if you're adding 64 numbers that are 64 bits each, you can add each of those 64 bits independent of all the other bits, until you get to that very last step where you have to use some kind of a ripple carry or carry look ahead adder. So the Wallace tree that we were drawing, which takes you to where you can add 64 bits in only, say, 7 sets of operations, that's something you do on each of the 64 bits in parallel. So you really go from like a 64 times 64 propagation delay down to about 7 propagation delays. Okay, it's a really huge savings, especially as your words get bigger. But it's the parallelism, it's the fact that you don't have to worry about what this bit's doing in order to add all of these bits. You just add them up and you save their carries, and then at the end, you put all the carries together in one step. So that was the take-home message that may have been missed. All right, we're going to talk about trees and graphs this week. We're going to start with trees, and we'll see this again in 222. We'll actually code up a lot of tree algorithms, and we'll use this in 223 for some of our projects. And trees are a really, really popular way to organize information inside a computer. We're going to look at them a little more abstractly in here, but you'll see all this and actually write code for it in another few months. So I want to talk about rooted trees. So trees have vertices and edges. A vertex is just, you can think of it as a point. An edge is a connection between two vertices. So this could be a vertex, this could be a vertex, there's an edge. This could be another vertex, there's an edge, this could be another vertex, there's an edge. So a rooted tree has one vertex called the root. It's connected. And if we're just talking about vertices and edges, that's a picture with vertices and edges. But it's not connected in the sense that there's no collection of edges that gets from, say, this vertex to this vertex. Whereas if I don't have these two vertices and edge, every vertex here, there's a series of edges I can follow to get to any other vertex. Okay, so that's an example of a connected graph. So a tree is a collection of vertices and edges. It has one particular vertex we call the root. It's connected, and it has no loops. So this is not a tree anymore, because starting at one vertex, I can follow edges and come back to where I started from. That's a loop. If there's no loops, then we can't get from one vertex back to itself by following edges. So if we call this the root, then this is a rooted tree. And so is this. You don't have to draw this. So it's a collection of vertices and edges. There's one vertex called the root. Everything is connected to everything else through a series of edges, and there's no loops. So that's a rooted tree. Yeah.
What is like an edge you can draw that'll make it a loop? That'll make a loop? Okay, just any.
Yeah.
All of a sudden,
All of a sudden, it's not a tree.
What's wrong with loops?
What?
What's wrong with loops?
Nothing. They just make it not a tree.
So, a single loop will make it not a tree, not
Right.
just not a moving tree.
It's not a tree, then yeah.
Oh, wow.
The problem with loops is that you can get stuck in them,
Well, yeah.
right? So if I want to visit every node, every vertex of this tree, I can start at the root and I can do that pretty easily, and we'll see algorithms for it. But if I have a loop, it's possible I'll start chasing my tail and visiting the same vertices over and over and over again, unless I do something to avoid that. So for trees, we just avoid loops. Now, when you have a tree with these properties, we can draw it a little differently. Typically, I would put the root up here, and I would put my edges descending down. So this would be this edge, this would be this edge, this would be this one, and then I would go down here and come down. And root. There's that one, there's that one. This could also come down here, and this can come down here, and it goes down to there. And it starts to look a little more like a tree, actually an upside-down tree. But it's the exact same information. It's the same set of vertices and the same edges connecting them. I've just rearranged it on the board. But as far as what's connected to what, those are identical trees. Question?
Okay, I guess I missed what the root was in the first tree, because I thought the root in the first tree was gonna be the, vertices with 4 edge coming off it.
Nope, I called this the root.
Would you call that one the root instead?
I can call
Oh,
anyone the
that would
root that I
change-
want,
That would change the tree.
but it would change the tree, yeah.
Okay, so what's the difference between a tree that does have a root and one that doesn't? Just, no,
It's just a designation.
Okay. Okay.
So vertices, I'll sometimes call them nodes. I'll actually get really sloppy and use both of these. I'll tend to call them nodes more often than vertices.
Like, is that routine?
Yes. It's a feature. So there are some vertices that we can call a leaf. So a leaf node. And let me get rid of my kind of distorted looking tree. this one.
Well, yes, the ones that have multiple other things coming off of it, or perhaps the ones with only one coming off of it, one subsequent edge. I'm thinking either the one with 3 edges coming off of it, or a node that has edges that only go on for one more after it.
So our leaves are gonna turn out to be here, 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 here,
Just the ending nodes?
and here, yeah.
Well, that's disappointing.
Yeah. So terminology, parent and child. So, if you draw your tree with the root up here at the top of your board, and you extend downward when you have an edge, then there's a relationship between nodes. We can think of this node as being the parent of this node, and we can think of this lower node as being the child of this upper node. So it's like an ancestor tree. And since this node's the parent of this one, and the root is the parent of this one, we could think of the root as being the grandparent of this node. Okay, we'll actually need that terminology eventually. So if you start from the root and you go down a path and find the children of the children of the children, eventually you get to a node that has no children. Okay, that's what a leaf node is. So the leaf nodes would be here, 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 here. Following the child-parent notion, the root of the tree is the unique node that has no parent. Every other node has at least one parent. Well, every other node has exactly one parent.
Because if it had 2 parents, then it would suddenly become a loop? Or if it was a loop, it wouldn't necessarily have a parent or child, would it?
Yeah, it would sort of violate this idea of, because now this node would have 2 parents, but
Would that make it a loop?
no, that doesn't make it a loop.
Oh, okay.
But I said we want to list everything below its parent.
Then could it have 2 parents if this tree was, say, had direction? Because if this is sort of like a tree with no direction, there is no...
There's an understood direction here, which is downward if you like.
Okay.
But if we add we can have directions on graphs.
Uh-huh.
But this is basically a particular type of graph. Graph is just any old collection of nodes and vertices, but we're putting constraints on it. And one of our constraints is that we're going to picture this thing as a root at the top, and every node connected to it is at a lower level. So, if we have another parent coming up, that's going to be something different.
So if you have another plan for a child, then it means it's loop, right?
No, but you can't have more than one parent. That's just the rule. And if you're the root, you have no parent. So we can define subtrees. Right, there's nothing in this that says you can't have another parent. That's just a new rule I made up. So we can define subtrees as a tree that's contained inside this larger tree. For example, I can pull this off and treat that as a tree. And this will be the root of that tree, and these will be the children, and these will be the leaf nodes. And I could treat this as another subtree. And in fact, I could treat this as a subtree, because you can have a tree consisting of a single node. That's the root. And so for any node, each of its children can be the root of a subtree. So there's a whole lot of subtrees in here. Right, there's a subtree, there's a subtree, there's a subtree, there's another, there's one, there's another, and so on.
Subtree has to go all the way out the leaf, or could I cut the subtree off?
I think we're always going to follow our way down to the leaves.
Okay, so you couldn't cut off the branches and make new leaves?
Possibly, but we're not going to really be interested in that. I mean, I think technically, well, no, that would change the structure. Like if I just took these two nodes, maybe that's a subtree. That's not what I'm going to mean by a subtree, though. All right, we can talk about the depth of a tree. Depth of a node. So the depth of a node is the length of the path from the root of the tree to that node. Length meaning the number of edges. So the depth of this node is 1, because we have one edge from the root to this node. The depth of this node is also 1, because we have one edge from the root. The depth of this node is 1, 2, 3, 4, 5, 6.
So I'm just going back to previous concepts. I remember when you talked about power sets, it was the set of all subsets in a set. If we were to look at a set of all subtrees of this tree, would the tree itself be contained in that?
Yeah, I think a tree should be a subtree of itself.
So there's the same number of subtrees as there are parent nodes in the trees, or is it parent nodes?
I don't.
Just the total number of nodes, not necessarily a parent node, because we can have.
Oh, because you can have a leaf node. Okay.
Yeah. So, is this notion of depth well defined? Or put differently, was it appropriate to say the length of the path?
Well, there's only one path for the node.
So how do we know that?
Because there's no loops.
Because there's no loops. Because if there was another path we could follow from, say, the root to this node by some other collection, that would give us a cycle, give us a loop. So there can at most be one path. And is there at least one path?
There's only one.
Yes, because
Variable.
it's connected, right? So connectedness and no loops gives us unique paths.
Can we go from another subtree to another leaf and count that, like from that side to this side?
You could, but that doesn't give you the depth. It gives you something else.
count the depth, we count the edges between the nodes, right?
You count the edges, so what's the depth of the root?
0.
That's 0. So we can talk about the height of a tree. And that's just the maximum depth. Maximum depth of its nodes. So each node has a unique depth. You look at all those depths, you pick the maximum, that's the height of the tree. Kind of like a regular tree, it's got one stem going way up in the air, that's what you use to determine the height. So I think this tree has height 6. I think that's the deepest node.
We're really enjoying how contradictory the notation is for this, because we have a tree which has the roots at the bottom,
Yes.
but the child is considered below the parent. Then we've also got the height, which works the other way around, going downward. Depth works, kind of, in this setup.
I think if you stand on your head, it's consistent with nature, though.
Can we call it a potato instead?
Yeah.
I mean, we couldn't call them like a roots or a...
Yeah, I'm thinking of the root as like the top of the tree trunk.
Well, no, you have to think of the root as the beginning of the tree where the tree
Yeah,
started.
flip it over, here's the
Like,
ground.
you can't grow a tree without its roots, so you can't grow this kind of tree without its
Right,
roots.
so that's what springs out of the ground, and it bifurcates or infurcates as it goes up. And the leaves are at the very end, there's no branches coming out of them. That's what these are.
It still doesn't hold for below, so if you flip it upside down, then all of a sudden the child is notably above the parent, even though it's considered...
Well, yeah, the trunk is the parent, and this big branch was its child, and this little branch was its child, and the leaf is
You
its
don't call
child.
that below, it's above.
It is, if you flip this on its head.
Exactly.
Yeah.
That's what doesn't make sense.
Well, no, but
It works.
it's one inconsistency, which is that we've got the root up in the sky instead of the ground.
It's not necessarily inconsistent, because if you look at the root structure of a tree, it almost exactly mirrors the
That's
leaf
true.
and the branch structure.
Yeah.
So you're just looking at the root system.
You're looking at the root system, or you're looking at it in Australia from North America.
So you don't put leaves underground.
So essentially what we learn is to understand anything that's restructured, you have to stand on your head.
Yes.
I know what happened. The guy who came up with this spent too long in a basement somewhere.
Yeah,
Hadn't seen any trees for a long time.
that's right.
He forgot how they worked.
Or they came in through the window and grew down.
This
Yeah.
makes sense now.
That's probably what it was.
Getting way too literal here. This is just root structures, we shouldn't get too literal.
All right, so now we're going to make our trees even weirder. That's not weird enough anymore.
I think it's about explode.
So we're going to talk about binary trees.
That's kind of a different kind of tree than a root tree.
It's still a rooted tree, but it's a particular type of rooted tree.
Every parent has 2 children, I guess?
At most.
Are all trees root?
I don't know.
That's what you think.
I mean, if you don't have a root, I assume it's still a tree, otherwise it's a redundant terminology. But I don't know the detail. So a binary tree is a rooted tree where each node has at most 2 children.
Wait, so that's not a rooted tree then, because that node right there has 3.
This is not a binary tree,
Oh, okay. Oh,
okay, because this node has 3 children.
I read that wrong.
Okay. But if we lose this and we lose this, that looks like a good old binary tree.
And they have 1?
You can have 1. This node only has 1 child over here. This one has, yeah, so this node only has 1 child. This node has no children. This node has 2 children. So at most 2 children. So since we only have 2 children at the most, we can call them the left and right children. Depending on which side they're on. And those children form the roots of left and right subtrees. So we can pick any node, and if it has a left child, that's the root of a left subtree. So this is the left subtree of this tree. This is a right subtree. So let's draw some binary trees. There's a binary tree. So how many vertices does this tree have? So A, B, C, D, E, F, G, H, I, J. Vertices. How many edges?
9.
I'm gonna assume that's consistent. Or, isn't that how it always?
The order you put the letters in is arbitrary, right?
It's arbitrary for now, yeah.
That'd be weird if there was a convention like that.
Yeah. So how many vertices here?
6.
6. How many edges?
5.
5.
5. Coincidence?
I think
Not
not.
the edges and the ones that are the vertices.
So I is not an edge. What's not an edge?
That's a vertex.
Oh,
That's a vertex. That's an edge.
oh.
I feel like that holds for any tree without a, well, no, without a loop. Any tree.
Probably true. And we proved it.
I don't really want to. If you're gonna do it anyway, sure, I'll participate.
How do you think we might go about proving it?
Induction?
Start at 1.
Using induction.
I think
Because look, here we have a tree, and for this tree, the number of vertices is 1 more than the number of edges. If I add another vertex anywhere, it's going to have to be connected to this tree, and it's going to be connected by exactly 1 edge. I don't know where that edge is going to go, but once I've connected it with that 1 edge, my number of vertices has gone up by 1, my number of edges has gone up by 1. So if this held for 5 vertices, it's going to hold for 6 vertices. Right, that's your inductive step. Declare that this is true for, if this is true for n vertices, prove that it's true when you add 1 more vertex. And then show a base case. Well, here's 1 vertex, 0 edges, that's my base case. So yeah, it's a pretty straightforward proof by induction. Without induction, pretty hard to prove.
it's just true for trees in general, not just by.
I think it's true for trees in general. I did it as binary trees in my notes, but I think you're right. It's for any tree, as long as you only have a single edge connecting you.
Which, if you have no loops.
Which if you have no loops. But if you allow loops, then technically this is also valid.
But it's no longer a tree.
But it's no longer a tree. But if you allow this, this property is not going to hold. All right, so number of vertices is always one. One less than, one more than the number of edges. All right, let's talk about balance. Balance is good. The idea that we're going to use binary trees for is basically for storing information and organizing information in a computer. And we're going to see ways to do things like search for a piece of information. And it's going to be really efficient to search in a binary tree if we sort it in the right way, if we organize the nodes correctly. But this is a tree with 7 nodes. This is also a tree with 7 nodes. In this tree, if I start at the root, I can get to any node by just making 2 hops at the most. I can get to either of these nodes in 1 hops, or I can get to either any of these 4 nodes in a total of 2 hops. Starting here, I could go 1, 2, and get to any of my leaf nodes. If my tree happens to look like this, it might take me 1, 2, 3, 4, 5, 6 hops to get to that leaf node. So in terms of organizing information, this is going to be more efficient than this, even though they're both binary trees. And we want a way to capture the idea that our nodes are clumped together in some way that keeps the total distance from the root to each node relatively small. And this notion is called balance. So this we would say is a balanced tree. This is not. And this looks really nicely balanced because it's symmetric. But if, for example, we only had 6 nodes, that's still a balanced tree. Because the maximum depth of my nodes is close to a constant. Okay, so here's the formal definition of a tree being balanced. A binary tree is balanced if the height of its left subtree, meaning the left subtree of the root, equals the height of its right subtree plus or minus 1. So it's got to be close to matching heights on the left and right subtrees.
What's with the plus minus 1 thing?
Um,
Why not completely matching?
It would still be balanced.
because this is still technically balanced. It's as balanced as we can get with 5 nodes. But this has a height of 2 and this has a height of 1. Well, this has a height of 1 and this has a height of 0. So we're not going to require them to be exactly the same, but they need to be within 1 of each other.
I would.
How was that supposed to be? Oh, because
I would say if you move one of the sub nodes off of the left side onto the right side,
Yes.
it would be even worse in terms of efficiency, because if you hit the right side, you only have to make one call, period. But if you hit the other side, you're going to be making two regardless.
Yeah, it will change the efficiency, possibly for worse, possibly for better, but as we start looking at how we're going to organize information, there's going to be reasons that we can't just pick this up and move it over there.
Because ones and zeros.
But yeah, overall, I think your efficiency is going to be maximum here, as opposed to always requiring you to go through two hops. So this is the definition of balanced. If the height of its left subtree is close to the height of its right subtree, and you're going to like this, its left and right subtrees are balanced.
We got
It's a recursive definition.
Tree. So.
Or the tree is empty. Has no nodes.
Sure.
Yeah, just one node, real balance there.
Yeah. So the tree is balanced if the left and right subtrees have heights that are close to each other, and the left and right subtrees are each balanced. Or if the whole tree is empty, if it has no nodes at all. That's a degenerative case, but that's our base case. Yeah?
Can left and right subtrees share nodes? Like,
No.
they can?
That would create a loop.
That would create a loop, because the left subtree you get by moving left, the right subtree you get by moving right. And if there's a node that's over here and over here, I could get to it that way or that way.
What if you took off the node on the right, and then
This
it
one?
branched off from the node on the left? Then would you have a left and right subtree of the root?
Like this?
Yeah.
Yeah, the right subtree is empty.
Oh, okay. I see.
So intuitively, it may not be easy to grapple with this definition, but a computer can do it really easily. Because we can write a recursive function called balanced that says, is the tree empty? If it is, it's balanced. If not, find the height of the left and right subtrees. If they differ by more than one, it's not balanced. If they differ by one or less, call yourself on the left subtree and the right subtree. And if both of those are balanced, then the whole tree was balanced. And we can do that because we know the height of the left and right subtrees are less than the height of the original tree. Right? The height is the path from the root to the furthest away leaf. And whatever the distance was from the root of the original tree, the distance from a child of that root is going to be one less. So our subtrees are going to have smaller height, which means each time we take a subtree of a subtree of a subtree, the height of that tree gets smaller and smaller until eventually the height is 0, which means it has a single node. And then when we look at the subtrees of that, they'll be empty and they'll be balanced by definition. Technically, the height of an empty tree is -1. It's like it's like 0 factorial. It makes things work out. But we've got plenty of time to get tripped up on that later. Don't get tripped up on it now. All right, so there's a recursive definition of balance. But intuitively, we can apply this and feel good about it. For example, this tree over here, my left subtree has a height of 0, or -1. My right subtree has a height of 1, 2, 3, 4, 5. So the left and right subtrees differ grossly in height. That right there tells you it's not balanced. But this also handles the case where we have something like this. So the left and right subtrees each have a height of 2. But that doesn't make it balanced by itself. We also need to know that this subtree and this subtree are balanced.
Height of 3.
The height is the depth, so the distance from here
Oh,
to the leaf is 2.
subtree.
The subtree,
The
yeah.
subtree. Oh, okay.
So the heights are exactly the same for both of these, but this tree itself is not balanced because its left subtree has a height of 1 and its right subtree is empty. That's actually a height of -1. So they don't differ by 1.
So the whole thing isn't balanced.
The whole thing's not balanced,
Oh, it isn't. Why?
even though the heights are similar.
It makes sense if you think about it.
It makes sense because if we organize 1,000 pieces of data like this, it's not really tree-like, right? It might take us 500 hops to get from the root to a leaf. And we're not taking advantage of the fact that we could have nodes up here and here, and so on. So a well-balanced tree is just kind of all smushed up so that it's like short and squatty and wide. That's what we want for efficient use of these structures. But that's the formal way of defining balance. So here's a theorem to leave you with. The number of leaves in a tree is less than or equal to 2 raised to the height of the tree. So here was our case of 7 nodes, and height equals 2, and the number of leaves is less than or equal to 4. It could be smaller than 4, we could lose this leaf, or we can add that and have 4, but if we want another leaf, we've got to make the tree higher. So we could have 5 leaves, but now the height of the tree is 3. So our theorem's saying maximum number of leaves is 8. I won't ask you how to prove that, but you already know how to prove it.
I think from here on out, how do we prove it almost always will be answered by induction.
Yeah, that's the right answer for a multiple choice. All right, so tomorrow we're going to look at binary trees. We're going to start looking at how we organize information with them. So we'll talk about binary search trees, how we actually store something like numbers in a binary tree so that we can do efficient searching and sorting and things like that. And this is where balance will turn out to be more than just an odd recursive definition. It'll actually tie into the efficiency of our algorithm. All right, so we'll start from there tomorrow. No class on Wednesday, and Thursday probably we'll start talking about graphs, which is the general version of trees.
The homework due tomorrow? Or?
Homework due tomorrow.
Not on Thursday?
No. I gotta have something to do over a holiday.
Do you know what we're